So this is 2.5 continued, part 2. If you think about from 2.4, we talked about conjugates. So we can have like complex zeros are conjugates, which means if they form in the form of a plus bi, a minus bi, these are conjugates, okay? So if we are trying to solve a problem, let's say finding a 4th degree polynomial function with real coefficients that has -1, -1, and 3i as zeros, okay? Because 3i is a zero and the polynomial is stated to have real coefficients, you know that the conjugate of -3i is also going to be a zero. It has to be. So we can look at our we can take our form and we'll say, all right, I've got my function. Maybe I have a number out front, but I know because my 0 is -1 that I have to have x plus 1, and I have a multiplicity of 2, so that's going to be written twice. And then because of my conjugates, I know that this is true, so I'm going to say x minus 3i. And then because the conjugate must also be true, I have x plus 3i as a 0 as well. So again, if we just assume that a equals 1 in this case, we can kind of plug in our numbers and start solving. So again, if I use the distributive property here, 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 I'm going to get f of x equals x squared plus 2x plus 1. And then when I do that same thing over here, again, my middle term is going to drop out. And I'm just going to be left with x squared, -9 plus or times 3i. -3 times +3 is -9. So I'm left with -i squared. But remember, I squared is really like a -1. So as I think about it, I'm actually left with x squared plus 9. -9 times 1 is plus 1. Square root of -1 equals I. -1 equals I squared. So I could find a polynomial given the zeros. So it's like I'm working backwards. So my final example, if I'm given those zeros, x squared plus 2x plus 1 times x squared plus 9. And now I have to do this one more time. So x squared times x squared gives me x to the 4th. Again, you're going to have like terms that you are going to solve. So again, if you x squared times x squared times 9, 2x times x squared, 2x times 9, 1 times x squared, and 1 times 9 will give you the final answer of So given the zeros, I can work backwards and find the original polynomial function. That's something you will be tested on. And so you also may have to factor a polynomial. So let's say that we have the polynomial f of x equals x to the 4th minus x squared minus 20. And you want to write the polynomial as the product of factors that are irreducible over the rationals. So a quadratic factor has no real zeros or is said to be prime or irreducible over the reals. So an example of this would be like, so sidebar, okay, we'll come back to this one in a second. No. Whatever. Go back. We're just going to delete it. Okay, so it's irreducible over the reals. So again, the real numbers. When we say x squared plus 1. Again, this is like saying x minus I, x plus I. This is different than, say, this example, x squared minus 2, which if we factor this out, we get x minus the square root of 2 over x plus the square root of 2. This is irreducible over the rational numbers, but it's reducible over the reals. So this is irreducible over rationals, but reducible over the reals. Okay, so again, notice the difference. We have an I versus an actual numerical value, okay? So if I look at my example, and I said it was f of x equals x to the fourth minus x squared minus 20, and I start factoring this out, I'm going to say, okay, by the time I factor this out, I'm going to be left with x squared minus 5 and x squared plus 4. These two are irreducible over the rationals because, again, when I solve it, I say x squared minus 5. What's this 0? I'm going to say, okay, x squared equals 5, square root, x equals square root 5, positive or negative. And then when I do this one, I'm going to get that negative 4 again. I'm going to take the square root of x squared, square root of negative 4. And I can see, okay, yep, they are irreducible over the rationals. So in completely factored form, okay, in my completely factored form, I would say, all right, my final answer is going to be x plus the square root of 5, x minus the square root of 5, x minus 2i, and x plus 2i. So this is as far as I can factor this down. F of x equals. All right, and our last example, okay, our last example is going to be finding the zeros of a polynomial function. We're going to use synthetic division. We're going to use it algebraically. And there's two ways we can do it. We'll do it algebraically and graphically. So take the function f of x equals x to the fourth minus 3x to the third plus 6x squared plus 2x minus 60, given 1 plus 3i is a 0 of f. So again, two ways to solve it. So because we know that we have this zeros of complex numbers always have conjugates. Okay, so that means we know that 1 plus 3i is one of our zeros, and 1 minus 3i is also going to be one of our zeros. So again, if I take what I know, my two zeros, and I multiply them together, 1 plus 3i times 1 minus 3i, I'm going to get, well, excuse me, so our zeros are going to be x minus 1 plus 3i, and then we're also going to have x plus 1 minus 3i. So again, seeing the difference right here and right here. So when I set these up, because this is what I have to do to find what I'm going to divide by using synthetic division or long division, up to you. So if I multiply these, x minus 1 plus 3i multiplied by x minus 1 minus 3i. I'm going to be left with, okay, if I start simplifying, I see I have to distribute this negative into both terms. So again, I'm going to have x minus 1 minus 3i, and then x minus 1 plus 3i. And so I see I have x minus 1 twice. So I'm going to say that that's x minus 1 squared. Again, I have it right here, x minus 1 times x minus 1. And then I have negative 3i times 3i, which is going to give me negative I squared. Well, we know that negative I squared is really like negative 1 times negative 9. So I'm going to be left with x minus 1 squared plus 9. Now we can simplify x minus 1. So x squared minus x plus 1 plus 9. Combine like terms, x squared minus 2x plus 10. So that's what I'm going to divide by when I do long division. So I'm going to take my whole equation, x squared minus 2x plus 10, and do x to the 4th minus 3x to the 3rd plus 6x squared plus 2x minus 60. I know that to get an x to the 4th, I have to have x squared. So I get x squared, which gives me x to the 4th minus 2x to the 3rd plus 10x squared. Start simplifying. Again, you're subtracting this, so all of your answers are actually going to be negative. So this negative 2x turns into a positive. This turns into a negative. So I'm left with negative x to the 3rd minus 4x squared. Bring this down, plus 2x. I know that, and if I have an x squared, in order to get an x to the 3rd, I need to multiply it. So I'm going to say, okay, again, everything inside of here is going to be subtracted. So negative x to the 3rd, this is going to be plus 2x squared minus 10x. Again, this negative gets distributed and flips my sign in there. So I'm left with negative 6x squared plus 12x. Bring this down, minus 60. And I know that if I have positive x squared and I need to get negative 6x squared, I'm going to subtract 6. Again, put your parentheses. This is negative 6x squared plus 12x minus 60. After distributing and changing your signs, you're left with 0. So we are so close to being done, okay? Again, we already know that, hey, we factored this out. This gives us one of our solutions, and now we've got our second one. So if I were to say f of x equals x squared minus 2x plus 10 and x squared minus x minus 6. I could factor this out as x minus 3, x plus 2. Still have x squared minus 2x plus 10 out here. Therefore, we can conclude that when we solve these, okay, again, we get our x equals 1 plus 3i, x equals 1 minus 3i, x equals 3, and x equals negative 2. That's solving algebraically. Let's think about this with graphing, okay? If the original problem says you are given this 0, okay, we know it's got a conjugate. We already knew that. So guaranteed, I know, hey, I already have a 0 of 1 plus 3i, 1 plus 3i, which also means I have a 0 of 1 minus 3i because complex numbers come in pairs. Now I'm going to go to Desmos, and I'm going to graph this. Graph my function, x to the fourth minus 3x to the third plus 6x squared plus 2x minus 60. And hey, there's a 0, there's a 0. So using our graphing calculator is actually way easier, because if I understand what conjugates do, I also know, hey, this is -2 and this is 3. So given that I was given one of these problems or one of these answers right here, okay, it told me that in the problem, I use my knowledge of conjugates to understand, hey, if I have 1 plus 3i, I also have to have 1 minus 3i. And then I used my graphing calculator to help me solve and get those answers much, much faster.